Magnetic fields occur almost everywhere in the universe. Magnetic stones were already known in ancient Greek times. With such lodestones, the Chinese discovered around the year 1000 the magnetic field of the Earth. This field is created by dynamical processes in the fluid core of the Earth, in which the Earth's rotation plays an important role. Because of this, the Earth's magnetic poles are near North and South poles, but do not coincide exactly. The magnetic poles drift by about 40 meters per day. Above 100 kilometers in the atmosphere, the Earth's magnetic field plays a dominant role. It produces the so-called magnetosphere. As shown in this animation, it shields us from the charged particles that make up the solar wind. The flow of the solar wind around the Earth's magnetosphere distorts it. Powerful eruptions on the Sun disturb the solar wind, and the Earth's magnetosphere reacts by producing the impressive northern light. Other planets in our solar system, in particular Jupiter and Saturn, also have magnetospheres. Recently, one has even been able to observe northern lights on these planets. The Sun also has a magnetic field. In sunspots, it is even 1000 times stronger than on Earth. Most structures that one observes in the Sun's atmosphere are related to magnetic fields. Magnetic field lines, rising as giant loops from the interior of the Sun, give rise to sunspots where they cross the surface. In the atmosphere above the surface, the magnetic field changes continuously on arrival of more field lines from the interior. In dramatic glitches, known as solar flares, the atmospheric magnetic field readjusts, propelling gas out into interplanetary space, while some of it falls back to the Sun. These observations show how complex the magnetic field in the solar atmosphere is. The solar wind blows the Sun's magnetic field into the solar system and beyond, into interstellar space. The winds of billions of stars, like the Sun, fill the entire galaxy with magnetic fields. But the interstellar gas itself, rotating around the center of the galaxy, also produces its own magnetic field by a dynamo process, such as those operating in the Earth and the Sun. This field is drawn out into loops along the spiral arms of the galaxy. In other galaxies, this kind of magnetic field is also seen by observations with radio telescopes. Galaxies seen from the side show that the magnetic field is confined to the disk of the galaxy. But in some places, galactic winds also carry it out of the disk. This magnetized gas fills the space between galaxies in so-called galaxy clusters. Because of its high temperature, it emits X-rays. Fast-moving charged particles produce radio waves, so that with radio telescopes, clusters of galaxies can be observed as diffuse clouds. In addition, this magnetized gas also rotates the direction of polarization of radio waves from sources behind the cluster. Simulations of these processes have been done with supercomputers at the Max Planck Institute for Astrophysics. This image shows the result of such a simulation. Cold gas is shown in blue, hot gas in red. Such simulations help us to understand how magnetic fields evolve together with the large-scale structure of our universe. This shows the evolution of a magnetic field in a cluster that is still in the process of its formation. Such simulations give rise to a better understanding of the processes which occur in these objects and help to interpret various observations.